SwayamPrabha. Digital India. Educated India.
Let us start this lecture with a thought process. The dance of desires creates a wave of worries around our mind that muddles the power of soul. People say that soul is having infinite power, but however we do not experience it, and according to me it is the desires that creates a wave of thought processes, thoughts that really spoils the power of soul. So, let us recall what we learnt in the last lecture. In the last lecture, we basically initiated discussion how to analyze the cooling system, and we looked at that the flow situations and the heat transfer being conjugate in nature are quite complex to analyze analytically. Therefore, we consider the analysis by making very crude assumptions that we are considering the heat transfer problem to be one dimensional and steady, and that can be valid only when the area across the wall, both the hot side and cold side is same, and that is possible only when the radius of curvature of the combustion chamber and the nozzle is quite large. But today we will see how can we use this one dimensional steady analysis for complex practical configuration. As I told just now, we can really use it provided the area we can introduce into this expression so that the area on the both the hot gas side and the coolant side can be taken care, and we know that this area will be different. It is not same as we had considered earlier. Only in the flat plate that area will be same, and if the however, in our rocket engines there will be a circular shape or any other shape kind of thing. So, therefore, area cannot be really same on the both the side. So, therefore, this one dimensional steady flow analysis can be extended to complex configuration by considering effective area on the both hot gas and coolant side as given below. So, what we will be considering? We will be considering this A g is the hot side area, and A w is the area of the wall. Of course, we will have to take the average area having certain thickness, and S c is your coolant area. So, A g is the hot gas side area, A w is the effective wall area, and A c is the effective coolant wall area, that we will have to consider. And if we know this, then equation 8 becomes basically H dot double dash is equal to H g T w A minus T c plus H dot double dash R divided by H g divided by the resistances. This is 1 by H g, and we are saying that delta L by K w into A g by A w, and H g divided by S c and S c, and this we can call it as equation 9. and this you can derive yourself. I am just left for you as an exercise. In order to use this expression, we need to either know the heat flux, or we will have to also know the other things on the right hand side, like for example, T c we can fix sometimes for designing, and of course, the area has to be calculated, delta L can be chosen for design purposes, some thickness, or it is already designed. So, you know K W is the thermal conductivity wall, which we will have to find out depending on its material. And H g and H c, this is your convective heat transfer coefficient, has to be known, then only you can find out how much heat flux is passing through, or vice versa. If heat flux is known, then you can find out what will be your T W A or T T G or something like that. So, therefore, question arises how to determine the convective heat transfer coefficient. For this, we will be using basically semi empirical results expression for Nusselt number, which already people have done by conducting experiments. But however, if you want to do analytically, you will have to solve all the governing equations for conjugate heat transfer and turbulent flow, or if you want to do for one dimensional, of course, one can do that, but you may not get a very accurate result. Now, that can be done, as I told, by using semi empirical relation for convective heat transfer coefficients. And let us look at a heat transfer coefficient in terms of Nusselt number. This is your NUG, this is your gas side Nusselt number. Of gas, and which is nothing but Hg dg divided by Kg, and Hg is your gas convective heat transfer coefficient, and d is your diameter of the combustion chamber or the nozzle at any cross section on gas side, and this is your thermal conductivity. The Nusselt number is equal to 0.026 Re g power to the 0.8 and Prandtl number of the gas power to the 0.4, and this Re is your Reynolds number, that is rho V d by mu. This is your basically Reynolds number, and this is your Prandtl number. Keep in mind that this is a very important expression, and which will be using to evaluate the heat transfer coefficient on the gas side. Let us consider it little further and see what inference I can draw. And this is, as I told, this is your Reg is the Reynolds number, and Prg your Prandtl number. So, and Dg is your hot gas side diameter. And let us look at this expression little carefully, and let us say this is B 10, and if you look at Hg is basically proportional to, if I consider as a rho V d power to the 0.8 and dg. This is of course corresponding, and we know that rho V is nothing but your mass flux, that is g. this is your mass flux. This is, you can say, G is equal to Z. And I can say this is for your mass flow rate divided by area, that is your pi by 4 dg square. And for a constant mass flow rate, I can consider that as basically dg and 1 by dg square power to the 0.8 divided by dg. So, this is proportional to dg, right. This is proportional to minus 1.8. And this is a very important statement you can look at. That means that Ag is goes by 1 over dz power to the 1.8. This is a very strong dependent. That means Ag, if you look at Ag will increase if dg will be reduced, and which will be in case of throat area for throat, that is the minimum dg will be minimum, That means heat transfer by the hot gas throat of the nozzle will be much higher as compared to other regions. And therefore, one has to be very carefully design so that the material won't be get eroded due to the high temperature caused by the higher heat flux. So, let us look at another aspect of it. If you consider this Ag, Ag is basically proportional to rho g of 0.8, and for an ideal gas I can say that it is proportional to pressure of chamber for a combustion chamber power to the 0.8. That means the cooling problems will be very much severe when the chamber pressure is increasing. That means at higher chamber pressure, that cooling requirement will be much higher. So, therefore, one has to look at it, and beside this you keep in mind that the rho and mu, k, and also the Cp, these are functions of temperature, and the temperature will be changing particularly in the nozzle to a larger extent from 3500 to maybe 800, 900 or 700 Kelvin. So, therefore, these properties will be changing. Now, question arises where you will evaluate its values, and what is being done that it is evaluated at the film temperature. So, these properties are evaluated at film temperature, Tf, and that of course one can say in different way, but we will be using this formula which will be useful, that is Tg plus Twh divided by 2. So, you can say that this is your wall and this is your temperature. If I consider this as a temperature, and this temperature is the TWH and this is your TG. Now, there is a variation in the wall itself, and that is true also in case of your combustion chamber or in case of your this thing. That means, where you will evaluate here or here, then you take some average temperature here. This is your film temperature. So, therefore, that one has to take care of it for evaluating the properties, so that you can get a proper estimation of gas convective heat transfer coefficient. So, let us look at a semi empirical relation for convective heat transfer coefficient of the coolant, and that will be using, this is NUC, it is similar to that. Nusselt number for coolant is equal to SC dC divided by Kc, which is nothing but 0.023 Reynolds number power to the 0.8 and Prandtl number is 0.33. If you look at this is a little different and coefficient is different, otherwise expression of the Nusselt number for both gas side convection and the coolant side convection is almost similar, I can say. And this is the Reynolds number, right. If you look at these are expressed as Reynolds number, and this is your Prandtl number. And if you look at this, we can also look at little different way now, and I can find out this is SC is basically equal to 0.023 rho V d by mu C and 0.8 and rho C p k, sorry, this is mu, that is your Prandtl number, C 0.33. And if I divide this by rho C V c and C p c, if I divide also the right hand side, I can say this is nothing but your rho C V c, and this is your 1 over C p c. And keep in mind that this is nothing but your the heat thermal capacity, this is known as thermal capacity of the coolant. You are considering this as a ratio of heat transfer coefficient of coolant divided by the thermal capacity of the coolant, and this term is known as Prandtl number. And this is a non-dimensional number, and which is being used in the heat transfer problem, particularly when the Reynolds analogy is valid. And keep in mind that this we can write down that SC, then we can write down SC by rho C V c C p c is equal to, and I can take this rho C V c and then find out, and then mu also. If I consider this mu as basically, if I consider 1 by mu 0.8 is equal to 0.2 by mu, I can use that from here. And then you can find out, if I take this rho V c here, then it will be nothing but your rho V c minus 0. This, and already we will have to take, I have not taken care of that, that is here, that is SCDC. That means this will be Kc, right, and also this will be 1 over dC. So, if you look at that, then you will find out this is nothing but your d power t minus. So, that becomes 0.023 rho v d by mu power to the minus 0.2, and if you look at this mu C p and K c, and this is K c. So, therefore, K c in the denominator it will be basically 0.67. So, all these things together, if I look at like 1 over and mu C p by this will be of course C, this is 0.33 is equal to is K c, and C p c is equal to, you can look at, this is nothing but your mu C p K c power to the minus 0.67, right. So, you can see this is basically mu C p by K c power to the minus 0.67. So, let us look at this, what we can infer from this. For to have a higher SC, what I will have to do? Basically, we will have to increase this rho Vc, rho C Vc, on also we can increase this CPC, and CPC can use by the coolant itself. For example, hydrogen being preferred over the others because it is having higher Cp values, and particularly for a fixed Reynolds number and fixed, see this statement that higher heat transfer coefficient for coolant or for even gas, that can be achieved by increasing the CPC for a fixed Reynolds number and Prandtl number. Consider this is your throat area, and at the throat generally this area is heat flux will be very high, and there will be heat flux here is very high, heat flux, and in order to protect this material, heat has to be taken away by the coolant, and for that we can increase this rho Vc, that means by rho Vc, and for a particular coolant, and density of the coolant cannot be changed. However, Vc can be changed, Vc can be increased, right, by decreasing the area for a particular mass flow rate. That means, Vc has to increase for fixed mass flow rate of coolant by basically decreasing the area, by decreasing the area of the coolant, and generally the Vc in the range of something 15 to 25 meter per second is being used at the throat region of nozzle. So, we will be can learn from here that how we can really use this expression and draw very simple and design considerations so that we can design the coolant passes properly, and so also the cooling system. Till now we have not really discussed how this adiabatic wall temperature is to be estimated. Let us look at that, and how we can really relate this adiabatic wall temperature and to the recovery factor. And recovery factor is really very important one, provided the velocity is very high, particularly in the nozzle where the velocity will be supersonic, and this is your adiabatic wall temperature, when this heat flux, you can consider that as a basically heat flux. I can, in our terminology what I am using, this is basically is equal to 0 heat flux along the wall, then we will get T W. However, this T W A and will be same as that the T G or not, but if you consider this is your total gas temperature and which is little lower than that of, and because this adiabatic, this velocity of the hot gas will be coming to the 0 at the wall. As a result, it will be having certain amount of the decrease in the static temperature due to the higher velocity gradient. And as this is having a higher values and this T G, therefore, this fluid will be at a lower temperature and there will be heat transfer from this. So, this high temperature, that there will be a little increase in the temperature. Now, this is of course possible only when you are having a very high velocity of the gas. To take care of that, we will define a recovery factor, which is defined as T W A minus T G divided by T T G minus T G. And as I told, T W is the adiabatic wall temperature, V G is the hot gas velocity and T G is your gas temperature, and T T G is your basically total gas temperature. And if I can assume these factors, then I can find out if I know T G, T T G and T G, T W A, or other way around, that means if I know this T W A and other temperature on the right hand side, I can find out recovery factor. So, let us look at how we can really find out this and use this recovery factor, but keep in mind that this can be used only when the velocity of the gas is very very high and it is coming to the standstill to rest on the wall surface, then only there will be increase in temperature and it can be utilized. For subsonic flow, RF is equal to 1, while for supersonic flow the recovery factor will be less than 1. As it can be indicated in figure that basically T W A is less than T T G. So, therefore, it will be less than 1 for supersonic flow. And let us take an example to illustrate this point. In a supersonic flow exhaust nozzle of a rocket engine, total temperature is 3000 Kelvin throat. If the recovery factor is found to be 0.91, flow is considered to be choked, particularly in this nozzle throat, and determine the adiabatic wall temperature by considering gamma of the hot gas to be 1.5. So, if you look at, we know this RF factor, what is given is the total temperature. This is T T G is given 3000 Kelvin and T G is not known and RF is allowed to find out. But how we will get this T G? T G we can get because it is choked condition, that means throat is choked, therefore, we can use the choked condition that is T G star is equal to T T G 2 divided by gamma g plus 1, gamma is given, T G is given. So, we can find out 2666 Kelvin, and this is now known and T G is known and RF is known. So, we can find out T W A is basically 2970 K, whereas the T G is something 3000 Kelvin, which is very closer, and you can find that the difference between T W and T G happens to be within 1% error, which will be within the experimental error. Therefore, we will be all the time considering T W A is approximately equal to TTG. So, hence we can assume TWA to be equal to TTG at the throat of the nozzle for this problem. However, for all the cases we may consider without incurring much error. Thank you very much. With this I will stop over. In the next lecture we will be discussing about the hybrid rocket engine. Thank you very much.